and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 9, Lesson 4 on parallelograms. Now as we talked about in the last lesson with trapezoids, right, there are many different types of specialized four-sided figures. And the one that we're going to talk about today may be the most important of them all, the parallelogram. So let's get right into it and first learn what a parallelogram is. All right. Many different special types of four-sided figures known as quadrilaterals. One of the most important is a parallelogram. So what is a parallelogram, right? A parallelogram is any quadrilateral that has exactly two pairs of parallel sides. It must have exactly two pairs of parallel sides. And those sides have to be opposite of each other on opposite sides of the quadrilateral, otherwise they would intersect if they were sitting beside each other. So similar to what we did in the last lesson with trapezoids, where we want to begin is have you look at a variety of different figures and try to determine whether or not they're parallelograms. So let me just bring up exercise 1 to the top of the board, and let's take a look. Of the figures shown below, circle any that appear to be parallelograms. Mark the pairs of parallel sides with arrows to show the parallelism. That's a mouthful of word. Parallelism. Try to say that like 10 times fast. Anyway, so let's take a look at the first figure in letter A, right? So one thing that we hopefully are able to tell in figure A is that this side is parallel to this side. So that's one pair of parallel sides. The problem is the other pair, right, would eventually intersect somewhere up there, and so that's not parallel. Those two sides aren't parallel. Because this doesn't have two pairs of parallel sides, we cannot say that this is a parallelogram. We just can't. Now let's take a look at figure B. Now in this case, this side and this side are parallel. If I extended them forever in two directions, they would never touch, so I can mark those. But likewise, this side and this side are also parallel, which I'm going to mark with a double arrow. All right, so this is in fact a parallelogram. One pair of parallel sides, another pair of parallel sides. So here's what I'd like you to do. I'd like you to take a look at the remaining four figures, mark off sides that you think are parallel, and then circle any choices that appear to be parallelograms. Pause the video now and go ahead and do this. All right, well, letter C has like nothing. No pairs of parallel sides at all, so that is definitely not a parallelogram. Now letter D, you might look at it and go, that's a rectangle, so it can't be a parallelogram. But again, a rectangle is a type of parallelogram, and this one certainly is. These two sides are parallel, these two sides are parallel, so definitely a parallelogram. All right. Letter C, we don't have any pairs of parallel sides. That side's not parallel to this one, that side's not parallel to that one. No parallelogram there. And finally, letter F is most certainly a parallelogram. That's a very specialized one. It's called a rhombus because all four sides are the same length. But that's kind of irrelevant. The only thing that matters to us is that those two sides are parallel and those two sides are parallel. So, also a parallelogram. 3 out of the 6 were parallelograms. I think 3 out of 6. Yep, B, D, and F. All right, so we have to be able to recognize a parallelogram when we see one, right? And the plain fact is, parallelograms are just trapezoids that have the extra property that they have two pairs of parallel sides. There's a hierarchy in geometry in terms of four-sided figures, kind of like in biology there is with things like, animals, mammals, different types of species within mammals, things like that. The broadest category are quadrilaterals, any four-sided figure. So any of these figures are quadrilaterals, right? But then we have the trapezoids, which have either one or two pairs of parallel sides. Now, if they only have one pair of parallel sides, they might kind of look like this, right? With this side parallel to this one, and in this figure, this side parallel to this one. Trapezoids that have two pairs of parallel sides, well, those are parallelograms. And they include kind of your garden variety of parallelogram. They include things like rectangles and squares, and then here's that thing that I called a rhombus earlier. All right, so there's lots of different types of four-sided figures. The ones that we're going to concentrate on today are parallelograms. So let's start to explore how we can find the area of parallelograms that aren't just simply rectangles and squares, because I think we already know how to find the area of a rectangle and the area of a square. Here we go. We can find the area of a parallelogram by breaking it into rectangles and right triangles as we did for trapezoids in the last lesson. So let's see how we do that in exercise number 2. A parallelogram has a base whose length is 12 centimeters and whose height is 5 centimeters, as shown. The parallelogram has been decomposed into 2 identical right triangles and 1 rectangle. Find the area of each of the basic shapes. All right, so again, let's just be very clear, right? We've got this sort of inner rectangle, and then we've got a right triangle and a right triangle that are identical, all right? Now, it's important to note that I've kind of done a bunch of the decomposing already, and we know that the entire base length of the parallelogram is 12 centimeters. And I'm telling you that this length, right, the base length of the rectangle is 8 centimeters. By default, of course, what that means is it means that this length must be 4 centimeters, and this length must also be 4 centimeters. So what I'd like you to do now is I'd like you to figure out what the area of the rectangle is, what the area of the 2 triangles are. That's letter A. So pause the video now and go ahead and find those 3 individual areas. All right, well, the rectangle is pretty easy. It's got dimensions of 8 and 5. So the rectangle's area will be 8 times 5, and that will be 40 square centimeters. All right, great. Now, triangle 1, right here. It's got a base length of 4 centimeters, and it's got a height of 5 centimeters. So its area is going to be 1/2 times 4 times 5. Right, we can do the 1/2 times 4 and just get 2 times 5, and that's going to give me 10 square centimeters. But whenever we decompose a parallelogram in this way, the 2 triangles that we have are identical to each other. And if you'd like, you can go through the same calculation to find the area of triangle 2, but it's going to be identical to the area of triangle 1, so I'm going to put down 10 square centimeters again. Now, area measures the space inside of a figure. So if I now want the space inside of the entire parallelogram, the area of the parallelogram in letter C, I can find that very easily by just adding up these 3 individual areas. Let's do that together because it's simple enough, right? 40 plus 10 plus 10 will give me 60 square centimeters. And that's it, right? Simple. If you joined us for our last lesson on trapezoids, this will feel awfully familiar because this is the way we found the area of all the trapezoids. There's really hardly anything different here. Maybe the one difference is that every time you decompose a parallelogram into a rectangle and 2 right triangles, those 2 right triangles will be identical to each other. All right? So let's keep going and do another one of these problems where we find the area by decomposing the parallelogram. All right, here we go, exercise number 3. A parallelogram with a base of 14 inches and a height of 10 inches is shown below. As before, the parallelogram has been decomposed into 2 identical right triangles and 1 rectangle. Find the area of the parallelogram. Fantastic. I'd like you to pause the video now and see if you can figure out how many square inches fall inside of this figure. All right, well first, let me do a little bit of additional dimensioning, right? Since we know that the base of the rectangle is 11 inches long and the base of the parallelogram is 14 inches long, then that's going to tell us that this must be 3 inches, come on, and this must also be 3 inches. Now I'm going to label this as figure 1, this is figure 2, and this is figure 3, so I can keep track of all my various areas. And let's start with the area of the first figure, triangle 1, which, right, its area is going to be 1/2 times 3 times 10. If I want, I can do the 1/2 times the 10 to get 5. and that's going to be 15 square inches. All right, for figure 2, its area is just that rectangle, which is going to be a base of 11 inches times a height of 10 inches, and that's going to be 110 square inches. And the triangle for figure 3 is going to have the same area as 1 because they're identical, and that's going to be 15 square inches. The total area, the area of the parallelogram, is going to be 110 plus 15 plus 15. For me, I like to add those 15s together first. That's going to be 110 plus 30, and that will be 140 square inches. All right. Now, one of the really cool things about parallelograms is that you can actually find their area in a much simpler way. And that's what we're going to look at in the next exercise. All right, let's take a look. Exercise number 4. Looking back both at exercise number 2 and exercise number 3, can you see an easier method for finding the area of a parallelogram if you know its base and height as shown below? All right, so let's talk about this a little bit. Right here, for exercise number 1, we had a parallelogram whose base was 12 inches and whose height was 5 inches, and we found its area was centimeters. A base of 12 centimeters, a height of 5 centimeters, and an area of 60 square centimeters. For the next exercise, exercise 3, we had a parallelogram with a base of 14 inches and a height of 10 inches, and its area was 140 square inches. Okay, so just looking at those two, can you write a formula for the area of a parallelogram whose base is given by the letter B and whose height is given by the letter H? Think about that for a minute. What would the formula be based on what you see right here? Well, notice, right? And again, here's where you have to feel very comfortable with your products. 12 times 5 is 60. 14 times 10 is 140. So it appears that we can find the area of a parallelogram by just doing the base times the height. That's it, right? So the area of a parallelogram appears to be just base times height, right? Now, letter B. Can you explain visually why the formula for the area of a parallelogram is the same as that for the area of a rectangle? Now, you might say to yourself, wait. The area of a rectangle was length times width. The area of a parallelogram is base times height. That's just what we're calling the letters, folks, right? Whether I'm talking about length and width, base and height, it's really two things that are perpendicular to each other, right? The base being one of the side lengths, and then the height being the distance between that side length and the one that's parallel to it, right? It's really the same thing as the rectangle. So can you see visually why that's true? Think about cutting this parallelogram up and rearranging it. Pause the video now and think about that a bit. Well, it's really quite cool, right? The plain fact is, I can take any parallelogram, slice down like this, giving me this right triangle, and then that right triangle could move over here along with the base, and now I have a rectangle that has a base with a length of B, a height with a length of H, and therefore it's got an area of B times H. Every single one of them can transform that way, where that right triangle could just be sliced off, put over here, not easy to do when I'm looking at the camera, and all of a sudden we have a rectangle instead, okay? So any parallelogram can be rearranged into a rectangle with the the same base and height. And there it is, right? It's really kind of cool. Maybe my triangle needs to move up a little bit, but that's it. So let's see how we can play with that a little bit with a parallelogram that lies in the coordinate plane. Exercise number 5. Parallelogram ABCD is shown graphed on the grid below. Letter A just asks us to state the coordinates of its vertices below. Fantastic. All right, so this is just some good practice, I'll be honest with you. I want you to be able to take a look at this thing and I want you to be able to tell me what the coordinates of A, B, C, and D are. Pause the video now and write those down here. Don't forget, the way you want to do that is by kind of putting down a little A with the parentheses, put its coordinates in, a B with its parentheses, its coordinates in, etc. Pause the video now and just come up with those coordinates. All right, well, simple enough. For A, we've got an x-coordinate of -2 and a y-coordinate of 6. For B, we've got an x-coordinate of 3, a y-coordinate of 6. For C, we've got an x-coordinate of -3, a y-coordinate of -8. And for D, I'm going to have to just sneak that in here. We've got an x-coordinate of -8 and a y-coordinate of -8. It's very important. This is the first year you've ever dealt with negative numbers in general, right? And that means it's the first time you've ever dealt with negative numbers on the coordinate grid. So make sure you've got that down. Now let's take a look at letter B. Find the length of the base and the height, and then calculate the area of this parallelogram. Right, so I don't want to carve this thing up. In fact, it would actually be quite difficult to decompose this parallelogram. But let's just draw another picture of it right here. All right. Now, what could I definitely figure out? One length I can definitely figure out about this poorly drawn parallelogram is the length of DC, which is the same as the length of AB, right? And I can see that both the length of AB and the length of DC or CD, however you want to call it, is 5 units, right? So that's what I'm going to use as my base. Now, what do I use as my height? Well, the height literally is going to be the vertical distance from here down to that line segment, assuming I've kind of extended it. So I literally want to just go from point B all the way down here, right? I want to know what this length is, and that length will be the height. So what do I have? Well, I have 6 units up to B, right? And I have 8 units down to C. So 6 plus another 8 gives me a height of 14. All right? And now that's all I need, because I just need my base times my height. So now my area is base times height, just like for a rectangle. That's going to be 14 times 5, and that's going to be 70. All right, we've discussed this before. You probably could leave it as just 70, but your teacher might want you to write down something like 70 square units. That's something you'll have to discuss with her or him. All right, that's it. So, parallelograms are very important figures, and they include such things as rectangles, squares, rhombuses, right? All parallelograms are trapezoids. Not all trapezoids are parallelograms. And what we found today was that, yeah, sure, you can still find the area of parallelograms if they've been decomposed into figures that you can then find the area of. But the great thing about a parallelogram is it actually has the same area formula as a rectangle. Side note, that's not that strange given that a rectangle is a parallelogram. So you'd think what works for a rectangle likely would also work for a parallelogram. And it does. The area formula for a parallelogram is simply its base times its height. The key is, unlike a rectangle, the base is most likely a length of the side of a parallelogram, but the height is the distance between two parallel sides and tends not to be one of the side lengths. All right, we're going to get a little bit more work on this in future lessons. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.